Okay, so in the last lecture we proved that there is a bijection between ideal class group of a number field k and equivalence classes of binary quadratic forms of discriminant dk. Okay. So, if you want to find out how many elements, distinct elements are there in the ideal class group of k, you can find the number of reduced binary quadratic forms of discriminant dk, and this we know how to do. So, we will see some examples of this today, and then we will also prove a theorem about order 2 elements in the ideal class group. Okay. So, here it is. Now, recall that a reduced binary quadratic form is bxy x xy plus cy squared. So, c has to be bigger than or equal to a, and this is bigger than mod b, bigger than or equal to mod b, and if an equality holds, so if c is equal to a or a is equal to b, then a is equal to mod b, then b can be taken to be bigger than or equal to 0, right. So, that is what a reduced binary quadratic form is, right. And so, there is a very, I think we did prove this, but anyway let me go over it. So, d is the discriminant, this is b square minus 4 ac, this is less than 0. And now you see that d, so if I put something which is yeah, I do not know. So, let us say instead of a I am instead of c I am putting a. So, I am putting something all right, let me write it like this. So, let me write minus d as 4 ac minus b square, right. So, if I am putting instead of c I am putting something smaller, then I will get that this is bigger than or equal to 4 a times a, and instead of b I am putting something bigger, like instead of mod b I am putting a, then again I am making this smaller. So, you know this thing. So, this is 4 a square, which means that sorry not 4, 3 a square, which means that a is less than or equal to square root of minus d by 3, right. And mod b is less than or equal to a, and this is less than or equal to square root of minus d by 3. So, what we do is we run through all b's like this. So, what we do is we run through all b's such that mod of b is less than or equal to square root of minus d by 3, okay, and find a and c using yeah, 4 ac equal to b square minus d, right. And another remark is that b has same parity as d, otherwise you will not have any solutions to this equation, right. B square minus d is divisible by 4, in particular it is even. So, whatever parity b square has, the same is the parity of d, all right. So, how do we do this? So, let us take an example. Find the number of elements in the ideal class group of k, where k is equal to q, let us say square root of minus 10, right. So, q square root of minus 10. What is the discriminant of k? This is minus 40, right, because that is the minus 10 is 2 mod 4, and so if you are taking q square root of m and m is 2 mod 4, then the discriminant is 4 m, right. And so we get mod of b is less than or equal to 40 square root of 40 by 3, which is definitely less than. So, 40 by 3 is 13 point something. So, square root of 13 is definitely less than 4, right, and d is even. So, we just have to consider even things, and so you try to solve. So, let us say take b equal to 0, then 4 a c is equal to 40, and so a times c is 10. And so, the possible values of a and c are a is equal to 1 and c is equal to 10, right, or a is equal to 2 and c is equal to 5, right. And you can't have anything else because a has to be less than or equal to c, okay. And so, there are two reduced binary quadratic forms here, which is x square plus 10 y square and 2x square plus 5y square. So, there are two of these. What about b equal to 2? Then you want to solve 4 a c is equal to 4 a c is equal to, so 44 . So, a times c is equal to 11, which means that a is equal to 1 and c is equal to 11. So, those are the two, that is the only solution, and so you get x square plus 2xy plus 11y squared, right. Yeah. So, there are three reduced binary quadratic forms of. So, there are exactly 3 reduced binary quadratic forms of discriminant minus 40. Hence, the number of elements in the class group is 3, and we know that there is a unique group of order 3. So, hence the ideal class group is isomorphic to Z mod 3Z, cyclic group of order 3, right. So, this turns out to be the easiest way of finding class groups for imaginary quadratic fields, all right. And we can do many more examples, but let us not worry about that. So, maybe I will just make some remark about how rich this theory is. So, Gauss had conjectured that there are only finitely many, and in fact, he gave a list of 11 number fields. In fact, only 11 imaginary quadratic fields with class number 1, imaginary quadratic fields K with CLK equal to trivial group, okay, with class number 1. So, he gave an explicit list, and this was proven by Heegner. This was proven by a number of people, but yeah, there were some weaker results, but this was essentially proven by Heegner completely. Heegner was a school teacher who was interested in mathematics, and he proved this conjecture of Gauss in maybe I think 1950s, So, more than 100 years after Gauss conjectured it. Yeah, but there are other results due to various people like Heilbronn and Davenport and Alan Baker and Brouwer and Ziegel, etc. So, in fact, the class number, so if Hk is the number of elements in the class group of K, then log of Hk, it grows roughly like half the log of discriminant of K, right. So, this is asymptotic growth, right. It does not mean that yeah. So, this kind of thing will tell you that there are only finitely many fields, but to prove that the list of Gauss was the exact list, it takes much more work. Okay. Yeah, and the other thing which is still unknown is how many what is the structure of the odd part of the class group of imaginary quadratic fields, and that's it seems to be cyclic almost all the time, meaning like maybe more than 97% of the time, but that is sort of conjectural. You can make a precise conjecture and then that statement is still conjectural. So, there is a lot of yeah, there are lots of things still to be discovered even about imaginary quadratic fields, although the class group of imaginary quadratic fields are perhaps easiest to study. On the other side, the class group of real quadratic fields, they seem much harder to study, and Gauss also conjectured that there are infinitely many real quadratic fields of class number 1, and that is still a conjecture. We do not even know that there are infinitely many number fields of class number 1, let alone real quadratic fields of class number 1. So, this other conjecture of Gauss about real class numbers of real quadratic fields is completely open, and it is one of the big mysteries of how to even approach it. So, the theory of binary quadratic forms, it does tell you something about yeah, I mean you can relate class group of a real quadratic field to binary quadratic forms, but in that case it is no longer true that any equivalence class contains only exactly one reduced binary quadratic form. So, there could be multiple reduced binary quadratic forms that are equivalent to each other, and so so getting this equivalence between class groups and binary quadratic forms, and then finding out how many, yeah. So, that will only give you some sort of upper bound if you, even if you write down a list of all reduced binary quadratic form, it will not give you the exact number. Okay. In any case, moving on, let me prove the following theorem. So, let K be an imaginary quadratic field of class number no, not class number, sorry, of discriminant dk. Okay. Let T be the number of distinct primes dividing dk, then the number of elements in CLK of order 2, so exact order 2 is 2 to the t minus 1 minus 1. Okay. So, here is an example. Right. If you take dk to be minus 40, then t is equal to 2, right. And so 2 to the t minus 1 did I make some error in computing that? Ah, sorry, this was wrong. Yeah, this part is wrong, and the reason is that if a is 1, then 1 is less than 2, right. So this is not a reduced binary quadratic form. Sorry. So yeah, that's okay. So there are exactly 2, and so this is in fact 2. Yeah, sorry about that. Okay. Right. So this part is wrong, right. Okay. All right. So I made a mistake here, and the reason is like I found it from this now, because this is 2 to the 2 minus 1 which is 1. So there is exactly one element of order 2. So hence CLK has exactly one element of order 2. Yeah, sorry about that error. Okay, so so let's look at one more example before we go to the proof of this theorem, right. Okay. So let's look at one more example. You take k to be q square root of minus 35, right. And so in this case dk is minus 35, because minus 35 is 1 mod 4, right. And so so you check for all b's which are less than 35 by 3, right, and 35 by 3 is 11 point something. It's certainly less than 12, and so square root of 12 is again less than 4, right. So you try with b equal to plus minus 1, and I should, yeah, I mean another error I made here is kind of b should be plus minus 2, but it does not matter because this is right. Okay, I should have been a little more careful about that. So I'll be more careful in computing this example now. So you take b to be plus or minus 1, then 4ac is b square minus 4 sorry minus dk. So this is 1 minus minus 35, so this is 36, right. And so a times c is 9, which means that a is equal to c is equal to 3, in which case b has to be positive, or you get a is equal to 1, c is equal to 9, in which case again b has to be positive, right. And yeah, so these are the only two binary quadratic forms, 3x square plus xy plus 3y squared, or x squared plus xy plus 9y squared, and that is it. So you can yeah, of course we have to try b is equal to plus minus 3, but in this case 4 times ac is 9 plus 35, which is 44, and then AC has to be 11, which means that A has to be 1, but 1 is less than mod of plus or minus 3. So there are no binary quadratic forms given by this thing. Okay. So again CL of K is Z mod 2Z, right. So this is what you would expect, and let us look at one more example, a bigger one. So I take k to be q square root of minus 131, and minus 131 is also 1 mod 4. So, dk is again minus 131, okay, and so mod of b is less than or equal to square root of 131 by 3. So, this is 43. So, this is certainly less than 7, right. And so, again I have to try for odd b. So, b is equal to plus or minus 1, then 4ac is equal to 132, which means that ac is equal to 20, not 20, 33, right, okay. So, then A is 1, B is 1 and C is 33, or A is 3, B is plus or minus 1 and C is equal to 11, and I think that is about it for this particular example. But you can also have B to be plus or minus 3, in which case 4AC is equal to 140, and so AC is equal to 35. So, 1. So, A is 5, B is equal to plus or minus 3 and C is equal to 7. So, that works, or you can have B to be plus minus 5, in which case 4 times AC is 25 plus 131 is 156, in which case A times C is 39, and the only factors of 39 are 1 and 1, 3 and 39, 1, 3 and 13, none of those are permissible, right, because A has to be at least 5, right, and C has to be also at least 5, okay. So, so there are no solutions here, which means that there are 1, 2, 3, 4, 5, right. So, yeah, so there are exactly 5 reduced binary quadratic forms, reduced binary quadratic form of discriminant minus 131, and so the ideal class group is isomorphic to Z mod 5Z, right. And again the number of prime factors of Z mod 131 is exactly 1, 131 is a prime, and that is why there is no element of order 2, right. This is what our theorem would tell us. Okay. Yeah, all right. Maybe there is not enough time to start the theorem. So, let me do one more example, an even bigger one. So, k is q square root of minus 229. So, this will, yeah, this is the first time where you can have two possible choices of what the group could be, and I think, let us see, is this the one or yeah, let me do another one, not this one. Let me do square root of minus 14, oops, minus 14, right. So, here discriminant is 4 times minus 14, which is minus 56, right. And so, Okay. So, B mod of B is less than or equal to 56 by 3, and what is this? This is less than 19, square root of 19, and so it is certainly less than 5, and so you can take B to be 0, in which case 4 AC is 56, which means that AC is 19. So, you get A equal to 1 and C equal to 19, or you can have B to be plus minus 2, in which case 4 AC, or yeah, let me write AC is 60 by 4, which is 15, and so A is equal to 2, sorry, not 2, 3. B is equal to plus minus 2 and C is equal to 5, or you can have B to be plus minus 4, right, and then AC is 1 by 4, 16 plus 56 is 72, which is yeah, 18, and so yeah, so there are no solutions here, but what did I do wrong? Ah, sorry, this is a, damn it, I did an, sorry, this should be 14. So, this is 1 and 14, or A is equal to 2 and C is equal to 7, right. And so, there are 4 reduced binary quadratic forms of discriminant minus 56, and so the number of elements in the ideal class group is precisely 4. So, there are 2 possibilities now, right, there are 2 possibilities for this group. So, CL of k is Z mod 2 cross Z mod 2, or CL of k is Z mod 4Z, right. So, which one is it? So, now you look at what T, which is number of prime factors, distinct prime factors of 56, this is equal to 2, right, and so 2 to the T minus 1 is 2 to the power 1 minus 1, which is 1. So, there should be exactly one element of order 2. So, hence by the theorem, CL of k has exactly one element of order 2, and so hence CL of k is isomorphic to Z mod 4Z, right. So, we can determine the structure of the group also if we use this theorem. Sometimes we can use this theorem and get the structure of this group. All right. So, I think we have seen enough examples on how to compute ideal class group of imaginary quadratic field using the theory of binary quadratic forms. Later on in the course, we will do a direct computation using Minkowski bound, then we will compute ideal class groups of not just imaginary quadratic field, but real quadratic field and maybe some fields of higher degree as well. In the next lecture, we will prove this theorem that I stated today about the number of elements of order 2 in the class group of imaginary quadratic fields. Thank you.